This is a massive block of pink Himalayan sea salt. It lights up like a lamp, tastes salty, and looks cool, but I've always wondered what causes it to have this pink color. Just by looking at it, we can see it has this ununiform pinkish red color throughout the chunk that varies in intensity. Even the pink Himalayan sea salt that's meant to be put on food isn't uniformly pink. There's specks of pink, red, white, and even some areas that appear crystal clear. The color observed in pink salt is actually from iron oxide, which is commonly known as rust. The different shading of pink Himalayan salt results from an uneven amount of iron oxide dispersed throughout the salt. As this type of iron oxide contaminated salt is formed in nature, we all know nothing in nature is perfect, proven by the weird colorations of the salt. My goal for this video is to perform some reactions and conduct some tests that prove the pink salt is actually coming from the iron in the form of iron oxide. As this salt is mainly composed of sodium chloride and tiny amounts of iron oxide, I can use this to my advantage to separate the two compounds. Sodium chloride is dissolvable in water, but iron oxide is not. Therefore, if I take a sample of this pink salt and dissolve it in a little distilled water, the sodium chloride should dissociate into the respective ions, leaving the iron oxide in the bottom unable to dissolve. As we can see, this little bit of pink dust at the bottom of the beaker is in fact our iron oxide. Because the iron oxide content in pink salt is less than 1%, I needed to dissolve a lot of salt and keep decanting it out just to get a small amount of this iron oxide. With iron oxide being a rather stable compound, our testing method that will come in a minute won't work on the iron oxide in this form. What we need is iron with a 3+ charge. And even though iron and iron oxide is already 3+, the bonding between the iron and the oxygen is just too strong. So therefore we need to break it. To break this bond between iron and oxygen, we can use a 2-molar solution of HCl that will protonate the oxygens, creating water and forcing the iron to form ferric chloride with the remaining chlorine ions. Although iron would rather form a compound with oxygen as it's more electronegative than chlorine, the protonation of oxygen leaves the iron with no choice but to bond with 3 chlorine ions. But that actually helps us out. After allowing this reaction to go on for about 2 hours with constant stirring and a little heat, I also let some of the HCl evaporate just by reducing the heat and letting it sit out for another hour or so. With this beaker now consisting of ferric chloride and water, we can use a compound called potassium thiocyanate to really tell us if iron is present in this solution. When we add potassium thiocyanate to the solution, we get a ligand exchange reaction where the thiocyanate ligand bonds to iron as opposed to the potassium, as the iron forms a coordination complex that potassium does not. In simple terms, iron helps form complexes where multiple ligands can bind to one metal ion due to its 3+ oxidation state, where potassium doesn't have it as it's in the alkali metal group and it has a 1+ charge. This makes iron thiocyanate a more stable product as opposed to potassium thiocyanate. If this is actually true, adding the potassium thiocyanate to our beaker of ferric chloride should produce a deep red color very similar to blood. As you can see, this reaction is indeed taking place, noted by the deep red color, proving to us that the pink color inside pink Himalayan salt is indeed coming from the iron in the form of iron oxide. If you enjoy videos like this, check out others on the channel.